Good afternoon, class. We are looking at chapter 5, integrals. Here, section 5.4, the substitution rule, part 2. So in the case of the substitution rule, you look for a function, you let u be g of x, and then you have the derivative g prime of x times dx. That's the idea. So the integral of f of g of x times g prime of x dx. G of x is a choice of u, g prime of x dx becomes du, and that's called the u substitution. Now the integral of square root of 3x plus 7 dx. 3x plus 7 is a choice of u. If you differentiate, you get 3. Therefore, du is 3 times dx. Now, I've shown you before the method by which I solve is to notice when you compare and contrast, you see that over here, number 3 is missing. And I'll show you what I do. I plug in the 3 and undo it. But in most texts, they solve for dx. So let's solve for dx. I want to show you this method also. So to solve for dx, you divide by 3. So you rewrite this as square root of u times du over 3. And square root of u is u to the power of 1/2. And you move on from here because this now requires the power. However, I just wanted to remind you the way I did that, I would rewrite this, and the way I would rewrite it next to dx, I notice number 3 is missing because 3 is a number, and you can only do that with numbers. You can throw in the 3, undo it with its reciprocal 1/3. Make sure the product is always positive 1. And I hope you see that this is identical to this. The difference is this is a tad faster, I believe. And so now using the power rule on this piece, 1 over 1/2 plus 1, u to the power of 1/2 plus 1 is 1/3 remains, and we have a constant. So 1/2 plus 1 is 3/2. This is 2/3. The product of these two is 2 over 9. So you get 2 over 9 u to the power of 3/2 plus a constant, where u is 3x plus 7. The final answer is 2 over 9, 3x plus 7 to the power of 3/2 plus the constant. Now, I want you to see both questions side by side because they both involve ln x. When ln x is involved, that's a choice of u. The derivative is 1 over x. Therefore, du is 1 over x dx. And I want you to see two ways of writing 1 over x dx or dx over x. They're identical, okay? So I'm going to, anytime you have a question like that, you are going to rewrite it. So I'm going to rewrite it so it becomes clear to the reader what we are dealing with. This is ln x to the power of 2. And this part, I'm going to write 1 over x dx like the first one, just so you see there are different ways of writing it. Now, if you recognize this as u squared du and you want to skip this step, you can. But I highly recommend you do that until you become very comfortable with that. Now, this follows the power rule, becomes 1/3 u cubed plus a constant, where u must be replaced with ln x. Bear in mind, 1/3 ln x to the third power plus c means ln x times ln x 3 times. This is not the same. So ln x to the power of 3 is not the same as ln of x cubed. Don't mix them up. This is the same as 3 ln x, okay? So do not mix them up. All right. So what about part B? We are going to rewrite it again in a manner that part B becomes clear that it's 1 over ln x times dx over x. This time I showed it in this manner because they are identical. I want you to see various formats. So 1 over ln x, 1 over u, dx over x, du. And 1 over u follows the integral of 1 over x dx, which is natural log. So this is a natural log of u plus a constant, natural log of absolute value of u, and u is itself ln x. So ln of absolute value of ln x plus c, and we keep the absolute value because ln x can be positive or negative. So when ln x is involved, that is the choice of u. Du can be written in two different formats. What happens when sinusoidal functions are involved? And again, I want you to compare and contrast. In this case, you have one of them. You have either sine or cosine, not both of them. And the argument has an exponent. So the entire argument, including the exponent, that means x squared, is a choice of u. The derivative is 2x. So du is 2x dx. We move the x next to dx so the reader can clearly see that you have sine of u, but this is not du. What's going on? Again, you can solve for dx as many texts do, including yours, or the easy way out, when a number is missing, you can put it in there, undo it with its reciprocal. So we throw in two numbers, 2 and 1/2. Now this is sine u du, and of course the derivative of sine is cosine, but the integral of sine is negative cosine. So negative 1/2 cosine u plus a constant, where u must be replaced by x squared, and that's the final answer. So what happens when both sine and cosine are involved? Then the one that has the exponent is a choice of u without the exponent. Sine has the exponent, so that's a choice of u. What is du? Cosine x dx. So what you're dealing with is the integral of u squared dx. This entire thing is du. So u squared du. Following the power rule becomes 1/3 u cubed plus a constant. Replacing the u, the final answer is 1/3 sine cubed x plus a constant. To make sure we are comfortable with this, let's look at the same situation, but this time cosine is the one with the exponent. In this case, because cosine has the exponent, that's a choice of u. The derivative of cosine is negative sine, therefore du is negative sine x dx. And the method that I mentioned, this part would be du if it had a negative sign. It doesn't. So you can put a negative sign next to it and negative outside. The product of two negative sign is positive 1. So you put a negative next to sine x dx and you put a negative out. Now you're looking at minus the integral of u to the power of 20 du. And that follows the power rule again, becomes negative 1 over 21 u to the power of 21 plus a constant. You replace the u with cosine x, you get negative 1 over 21 cosine to the power of 21x plus a constant as the final answer. So that's how we do indefinite integrals involving substitution rule. What if we have a substitution for definite integral? Remember, definite integral, you have the integral of a to b f of x dx, which gives you some number. So the integral of a equals 1 to b equals 2 of 2x x squared minus 1 so quantity cubed dx. This is a number. But to solve this, you need a substitution. And so there are two methods. Return to the original variable, meaning whenever you're done with the substitution, you go back to the original variable and therefore original limits. You don't even have to know what the new limits are. Let's stick with that and then we go with the second method. Clearly, x squared minus 1 is more complicated. That's a choice of you. And the derivative is 2x. Therefore, du is 2x dx. And so we are going to rewrite this as x squared minus 1 quantity cubed 2x dx. So this is u cubed. This is du going from 1 to 2. And we don't know the new limits yet. We're going to stick with that. And we're going to figure out the limits later on. For now, we want to go back to the original variable. So this, again, uses the power rule, so becomes 1/4 u to the power of 4. And again, notice in both cases, I'm not writing the limits because the limits over here do not pertain to the new variable u, they pertain to the old variable x. So I'm going to replace the u with g of x, which is x squared minus 1, and I can use the original limits 1 and 2. If I plug in 2, I get 4 minus 1 is 3 to the power of 4 is 81. If I plug in 1, I get 0. So I get 81 over 4 as the final answer. And I'm done. However, we can keep track of the change of variable in the limits of integration, meaning when a is 1, find this one. You get 1 minus 1 is 0. So when a is 1, put it into u or g of x becomes g of a, x squared minus 1. If I plug in 1, I get 0. So the lower limit is 0 here. And put that upper limit back into this. If I put 2 here, 2 squared, 4 minus 1 is 3. So u is g of b, right? G of the upper limit, x squared minus 1 becomes 3. And so now this, which was the original question, now we can have the answer 0 to 3 u cubed du, or 1/4 of u, 1/4 of u to the power 4, 0 to 3. The point being, you can't use the original limits for u, but you can use it now here. So having said that, if I plug in 3, I get 3 to the power 4 is 81. 0 gives me 0, so I get 81 over 4. Normally, this gives us the result a tad faster. Either way is fine, but ultimately you have to learn this method too. So that means the following theorem. If g prime of x is continuous function on a to b and f is continuous on the range of u equals g of x, then the integral of a to b f of g of x g prime of x dx is the integral of g of a to g of b f of u du. In short, what it means is that just plug in the lower limit into the function u, find the new lower limit, the upper limit, find the new upper limit. That's all it means. Okay, so let's look at a simple example, see how that thing works. For example, here, the integral of 3 to 4x squared of 25 minus x squared. First, let's go with the substitution. Let u be the more complicated function, in this case, 25 minus x squared. The derivative is minus 2x. So du becomes minus 2x dx. Now I'm going to put the x next to dx. So I want it to become clear that we have square root of u or u to the power of 1/2, but we don't have du. So what is missing? Negative 2. Since negative 2 is a number, again, you could solve for dx, but this is faster. Plug in negative 2, undo it with negative 1/2. It's reciprocal. So now you have negative 1/2, the integral. I'm not going to write the limits of square root of u du. We're going to discuss the new limits in a moment, but for now, let's finish it. Go back to the original variable. So you have negative 1/2. This is u to the power of 1/2, and I hope you remember we've done this a couple of times. What is the integral of that? 1 over 1/2 plus 1 u to the power of 1/2 plus 1. The reason we don't need a constant because it's a definite integral. 3/2. This is 2/3. The product of these two numbers, negative 1/3. So what are the new limits? For now, we're going to ignore that. And we are going to go back to the original u and the original limits 3 and 4. So negative 1/3 u is 25 minus x squared to the power of 3/2, and then 3 to 4. So we can go back to the original function as a u and the original limits and evaluate them. We can evaluate them, we are fine. But I want to go to the new limits. I want to show you how easy it is to deal with the new limits. For example, right here, if I plug in 3, when I square it, I get 9. 25 minus 9 is 16. That's the new lower limit. If I put the 4, square it because 16, 25 minus 16 is 9. So those are the limits I'm going to use. So I'm going to keep the negative 1/3 outside, and then u to the power of 3/2 becomes 9 to the power of 3/2 minus 16 to the power of 3/2. So 9 to the power of 3/2 means square root of 9, which is 3, cube it, 27. 16 to the power of 3/2 means square root of 16. 4, cube it, you get 64. The difference is negative 37. The product of these two is positive 37/3, and you're done. So it's that simple, everybody. All right. Now let's see what we do. The same thing. The more complicated function 2x cubed minus 8 is a choice of u. The derivative is 6x squared. So du is 6x squared dx. We move the x squared next to dx, so it becomes clear everything is in order except number 6 is missing. So we are going to multiply and divide by. That means throw in 6, and it's reciprocal. Again, the product of the two is 1. You could solve for dx. This is faster, everybody. So we have 1/6 the integral of u cubed du. And again, I didn't put the limits. Now, you can go back to the original or come up with the new limits. As far as the new limits are concerned, it's very simple. So we plug in 0 in here. We get -8. If I plug in 2 here, we get 2 times 2 cubed minus 8, which is 2 times 8, 16, minus 8 is 8. So those are the limits. Now, using the power rule, this gives us 1/4 u to the power of 4 and 1/6 1/24 u to the power of 4 from -8 to 8. Now, I can go back to the original and say 1/24 2x cubed minus 8 quantity to the power of 4 from 0 to 2, or this one. This is a tad easier. Notice here's the reason, everybody. We put 1/24 and then 8 to the power of 4 minus -8 to the power of 4. Please understand, because the exponent is even, 8 to the power of 4 and -8 to the power of 4 are identical, their difference is 0. So that goes fast. The rate of growth of a fish population was modeled by the equation g of t equals 30,000 e to the power of -0.6t over 1 plus 5 e to the power of -0.6t quantity squared, where t is measured in years since 2000. And lowercase g of t is in kilograms per year. If the biomass was 40,000 kilograms in the year 2000, what is the predicted biomass for the year 2020, and rounded to the nearest whole number? First of all, the moment you hear the rate of growth, that represents the derivative of the function. So if the capital G of t, the antiderivative, so if capital G of t represents the biomass of a fish at time t, then the growth rate, capital G prime of t, is lowercase g of t, is this function. And so right away, this becomes the initial value at time t equals 0. So we take 2000 to represent t equals 0. So 2020 would be 20 years later. 2025 would be 25 years later. 2030 would be 30 years later, and so on. And so based on the accumulated change, the net change theorem, the amount of increase in the biomass after 20 years takes the integral of 0 to 20 lowercase g of t dt. And now you're going to replace the function. The reason I'm coming up with this question, because although we've done the net change theorem, because this requires now substitution I figured it's worth looking at it. So having said that, anytime you have a fractional format, the first step is to simplify if you can, and when you cannot, with the denominator, of course, without the exponent, is a choice of you. Now, I hope you realize the derivative of this one, of course, is 0. This one is itself times -0.6. So the product of these two, 5 and -0.6, is -3. So du becomes -3 e to the power of -0.6t dt. Now, when we look at the numerator, we have two choices. We can put the 30,000 out and say, okay, I need -3. I'm going to put -3 and divide by it. Or you recognize this as the product of -3 and 10,000. You keep the -3 and you put the -10,000 outside. Again, this is your choice. Ultimately, you need the substitution, and you have to figure out what's the methodology. Again, If you put this completely out, when you divide it by -3, you get negative 10,000 anyways. So you're looking at negative 10,000 du over u squared, and I'm not going to write the limits yet. We will figure out the limits in a moment, but I hope we've done this a number of times. This is 1 over u squared, or u to the power of -2. Makes it 1 over -2 plus 1, u to the power of -2 plus 1. This is -1, this is -1. So minus 10,000 times negative u to the power of negative. Again, I didn't put the limits, but what are the limits? Let's plug in. If you plug in 0 into u, gives you 1 plus 5 e to the power of 0, which is 1 plus 5 times 1 over 6. If you put 20, you get 1 plus 5 e to the power of minus 0.6 times 20, which is 1 plus 5 e to the power of -12. This part, everybody, is 5 over e to the power of 12, which is 0, almost 0. So these are the limits. Okay, so we have negative times negative, positive 10,000 over u, or 10,000 times 1 over u. And as I said, the lower limit is 6. The upper limit is precisely this number, roughly 1.000031, but for all practical purposes, it's really 1. So 10,000 times 1 over 1 minus 1 over 6, which is 10,000 times 5 over 6, which is this number. The initial value was this. When you add it in the year 2000, we had 40,000. So in the year 2020, we have this plus the 40,000. That's the final answer. I want to show you a second method, as we have done before. And the second method is to integrate this without the limits, which gives you 10,000 over u plus a constant. And u is 1 plus 5 e to the power minus 0.6t. And to find the c, g of 0 is 40,000. This is an initial value problem. This is a general solution. Now, with the help of g of 0, we're going to find one solution. So let's plug in 0. So 10,000 over 1 plus 5 plus is 40,000. Use a calculator, and you end up with the c. And the function, which is a general function, now becomes a particular function by replacing this c with 38,333. So for the year 2020, we want g of 20, which gives us the same answer. If you want for the year 2025, then replace it with 25. So that's the advantage of finding the general solution and then a particular solution using the initial value problem. Now, again, I thought it's worth looking at these two questions side by side. Both of them have a denominator and a fractional format. More specifically, we are dealing with a rational function. The first step is to simplify. We can't, in which case the denominator is a choice of u. If u is 1 plus x squared, du dx is 2x. Therefore, du is 2x dx. So the first one is clearly the integral of du over u. And that follows the format, resulting in a natural log, and u can be replaced with 1 plus x squared. 1 plus x squared is positive, is in fact greater than or equal to 1 all the time. You could drop the absolute value. What happens here You use exactly the same u and du, and now you have du over u squared. Again, the repeat of something we've seen many times. We know how to integrate this using the power rule by bringing u up, making it u to the power of -2, which is definitely now using the power rule. 1 over -2 plus 1 u to the power of -2 plus 1 on a constant. This is -1, so minus u to the power -1, so -1 over u. And so -1 over u, which is 1 plus x squared and a constant, -1 over u, which is 1 plus x squared, and a constant is paradox. And the integral of dx over x plus 3, again, as always, you're dealing with a fractional format. The first question is, can I simplify it? And if you can't, you move on. Notice the derivative of the denominator is 1. So if you choose u to be x plus 3, du is simply dx. One thing I want to add, if you have x and in any number, x plus 1, -1, plus 10, -10, plus 1/3, -1/3 makes no difference. X and a number, then that is the choice of u, and du is always dx. So it becomes the integral of du over u. Again, following the format, we end up with a natural log and a constant. We replace the u and we get ln of absolute value of x plus 3 plus c. We must keep the absolute value because this expression can be positive or negative, whereas this expression will always be positive, so you don't have to keep the absolute values.